Good morning, everyone. Hope you're having a great day so far. Hope you had a good long weekend. It's definitely nice to have an extra couple of days to the weekend, even though we had that unexpected dumping of snow on Saturday night. Um, my son is one that loves snow. I think I've told you before. So he woke up and he's like, yes. And everybody else in the house was like, oh, not again. But we did make the most of it. I think you've got to. We went out sledding, kind of got outside, had some fun. So just kind of had to do that, I guess. Um, anyway, today's goal is to understand Newton's second law of motion. And remember, last week we looked at the first law, which was that any object at rest stays at rest, and any object in motion stays in motion at the same velocity unless there's a force on it. So basically, something that's not moving is going to stay not moving until you act upon it. While something's moving, is going to stay at a constant velocity unless there's a force acted upon it. Well, let's try and figure out what kind of forces do you need to put on these things to make them move. And what's the difference if you have something large, something small? What is the difference? Well, let's take a look. Firstly, let's just define what Newton's second law of motion is. What is it? Oh, we can see right here. Newton's second law of motion basically just states that force equals mass times acceleration. So force equals mass times acceleration. So if you're trying to figure out, okay, I have this item and it has this much mass and it's moving at this rate or it's accelerating at this rate, what force do I have behind it? So that's why we have force equals mass times acceleration. Most people just remember it as F equals ma. Then if you remember that F equals force, or F stands for force, m stands for mass, and a stands for acceleration, then you can remember the whole equation up here. I also want to show you this on the left side. Remember we did this distance, speed, time triangle? You can use that triangle to calculate force, mass, and acceleration. So say if you have mass and acceleration, that means you can calculate force. Whoops. You can calculate force by taking your mass times the acceleration. However, if, say, you have the force and acceleration, well, you can calculate the mass then. So if you know how much an object's being pushed, that would be your force. If you know how fast it's accelerating, that would be your acceleration. So you take your force and divide it by your acceleration. Then you would get your mass. So you would find out the mass of the object. Okay, let's take a look at a couple of examples. So what is the importance? What's the importance of F equals ma? I'm actually going to switch over to a different program here, just so I can draw on it. First, let's actually pretend that we're doing this. If you've ever watched, it's an old Bruce Willis movie, and it's called Armageddon. And it's basically, there's this asteroid hurtling towards Earth, and they have this big plan, and they're going to go out and actually going to drill into the middle of it, and they're going to blow it up. We're going to think about the same thing, but slightly different. We're going to say, okay, what if we've got this asteroid hurtling towards Earth, and we're actually going to take a rocket ship out, and we're going to try and push it and stop that asteroid? Okay, we can do that using Newton's second law of motion. So I'm going to do this. I'm going to say F equals ma. Force equals mass times acceleration. Okay, I know, say you can calculate the mass of this thing just by its size and what it's made up of. And we're going to say its mass is 10,000 kilograms. Now, I can also say that we've measured how fast it's going. And let's just say, for simple kind of number crunching, its acceleration is 100 meters per second squared. So actually, every second it's accelerating by 100 meters per second. Now, what force are we going to need to apply to balance this out to get it to 0? Let's take a look. Let's plug our numbers in. Take our mass, which is 10,000 kilograms, and we're going to times that by our acceleration, which is 100 meters per second squared. And this is why I like nice simple calculations. 10,000 times 100 would actually just get us to 1 million. We can label it two ways. Kilograms, meters per second squared is one way. That actually nicely equals 1 Newton. We've heard of that before, and that's much easier to write. So we're just going to say that. So if we wanted to send, let's see, gonna send our little rocket ship out here. Let's give it some flames. There we go. My rocket ship is going to go, and we are going to push this asteroid back. Okay, we're going to need to do so with a force of 1 million newtons. So we're going to be able to kind of stop that thing in outer space. Okay, in reality, that's very simplified. In reality, obviously, there's lots of other factors coming in, like the Earth's moving around, so we wouldn't have to slow it down all the way. Also, there's lots of other factors as far as wind resistance. We talked about fluid friction. That's actually the same thing as wind resistance. But just for simple calculations, that's how you can use F equals ma. Let's look at another one quickly. Oh, I just realized I was actually working on this one earlier. So I'm going to erase and we'll start from the beginning quick. Okay. We've got this guy and he has these two large balls that he's trying to move. And let's just say the first one we can see is 400 kilograms. That's its mass. The second one is 40 kilograms. That's that one's mass. For argument's sake, let's just say that the force is the same in each one. And let's just do 40 newtons on each. So his force is 40 newtons in that direction. Now we just want to know the mass. Oh, sorry, we want to know the acceleration because we know the mass. So again, we can use our triangle, force, mass, acceleration. All right. So in this one, we do not know acceleration. So we can say acceleration equals, and let's take our force of 40 newtons and divide that by our mass. It's this one. And on this one, it is 400 kilograms. .40 divided by 400 is 0.1. And we know we measure acceleration in meters per second squared. So all of a sudden, this guy is accelerating at 0.1 meters per second squared. And that's why he looks like he's pretty upset there. He's pushing hard and not much is happening. Let's take a look at this side and see, why does he look so much happier? Well, acceleration on this side is the same, 40 newtons. And actually, let me do this. Just so we can see. Acceleration equals force divided by mass. Just because we can't see our equation from the other side now. So acceleration equals, we said 40 newtons divided by a mass of just 40 kilograms this time. And that's pretty simple calculation. Acceleration equals 1 meter per second squared. Okay, so not exactly fast, but a lot faster than this side. So what can we deduce by that? Obviously, bigger masses require more force to get them moving. Or if you apply the same force to a bigger mass than a smaller mass, it's not going to move as fast. How much? Well, we can see that this mass right here is 10 times this one. This one moves 10 times faster than this one. So there's that direct relationship. 10 times more mass will move 1/10 as fast. And conversely, 1/10 the size, 1/10 the mass will move 10 times faster than something else. Okay, that is really everything you need to know about Newton's second law. So you can stop there for today and take the exit ticket quick. There's one other thing you can also do. Remember last week I had you start doing those hands-on activities? You can finish those. I've kind of set that aside to do tomorrow on Wednesday. But if you want to get ahead, you can do so. I'm not quite sure what it looks like on your side. It may just pop up that you can just resume it. If not, you'll just need to go back into this section here. Go back into Remote Learning Week 3. And this is just our old stuff. We started this on Thursday. So if you go into Thursday, and then there's Newton's lab stations right there. If you submitted it, I unsubmitted it for you because I actually want you to finish station, all of the stations 1 through 15, but by Friday because we're going to go over the rest of them. Today, I had you finish off at station 6 last week. So you'll start station 7, and you'll do 7, 8, 9, 10, and 11. Now remember, if you don't have the stuff, just skip them. But I think it's worth doing. And hopefully you have the items, and each one should only take about a minute to do. Then remember, once you've done each of them, just write down your findings here, write down what you did in this one, and write down your observations. Remember, don't submit it yet. We will do Newton's third law of motion on Thursday, and then I will have you wrap this up on Friday. Okay, so remember today, just do station 7 through 11, and then you can be done. Oh, actually, I'm sorry, this is for tomorrow. So I assigned this for tomorrow, but if you want to get ahead, you can do this today. All right, if you have any questions, let me know. Otherwise, have a great day, and I'm sorry this video got longer than I meant it to be.